In this video, we're going to look at how to estimate derivatives from a graph. So before we get started on that, we need to talk about a few things. The first thing we're going to talk about is a tangent line. Now, you may recall tangent lines from geometry with circles, where we have a tangent line to a circle is this line that hits the circle in one point, so that's tangent. And then we had secant lines that would pass through at 2 points. Now, the definition for tangent of a function, tangent line of a function, is a little bit different. It's not quite as cut and dry, so this is for circles. The tangent line for a function is a line that intersects a function at some point, and I'll just call that point x naught, f of x naught, so an x and a y coordinate, with slope equal to the instantaneous slope of the function. At that point. Now, it has to be a little bit more specific because functions come in various things, and a function in general does not have slope the same way that a line does. So if I consider, let's just say, x squared, this tangent line, let's just say at this point here, will look very similar to the tangent line of the circle. It's going to be this line that brushes up against the curve, doesn't pass through the curve. That's a terrible tangent line. Let me try to draw that better. But you can see it hits at this point right here, and it goes in the same direction. The curve was increasing at a rate of whatever it looks like, steeper than maybe 1. And so we have our line increasing at that rate. But tangent lines don't need to follow all the rules we had for circles. So for instance, if I consider this cubic function, which I can get by doing x cubed minus x, or minus some coefficient times x, a tangent line here will actually hit the curve in 2 places, and there's only one tangent line I can think of that would not, the tangent line here at this saddle point, at the origin in this case. So this tangent line does hit the curve in 2 places, but you can see right here, I intersect the curve, and it's going at the same slope. I was very slightly decreasing right here. So it can hit the graph more than once. It can also pass through the graph. So the tangent line here, you see it's always on the exterior of the circle, always above the circle, except at the one point where we're intersecting. But that's, again, just sort of a lucky coincidence for circles. If I consider just x cubed, and I consider the tangent line here, well, you can see, of course, it passes right through the function at that point of intersection. So this is much more general. Now you can see this definition here still works for our definition of tangent line in a circle, still defines this here, but in general, I can't just say it hits the curve only once, brushes up against the curve, doesn't pass through the curve, but all those things don't quite work. One more term here before I flip to the next slide, normal line. And that's just the line perpendicular to the tangent line. At that point, we'll call it x naught, f of x naught. And you may recall seeing the term normal as in like normal force when you did physics, and that's the force perpendicular to something that we're pressing an object against due to usually gravity. Alright, so now we've talked about all of this, let's look at what a derivative is. And so the derivative is a function let's say not that. Let's say whose outputs are the instantaneous slopes of some other function. And when I say instantaneous slope, I mean slope of the tangent line. So let me put that in here. Slope of the tangent line. Okay, instantaneous slope. Now, the derivative function, so notation for this, can be written a couple of ways. If our original function was f, I can write the derivative function as f prime of x. If our original function was y, I can write something like dy dx. I could write the derivative of the f function as df dx. I could also write it as d dx of f of x. And these all are ways to show a function that represents the instantaneous slopes of the f or the y function. Now, something to point out here, this dy dx notation comes from our slope, so dy dx comes from slope, which is delta y over delta x. And as we get to a limit definition of derivative in a different video, we will more clearly show how we transfer from these actual positive, or not positive, but non-zero, especially for delta x, steps to these infinitesimally small dy's and dx's. We'll get to that later, though, in a different video. Alright, so that's the notation for the function. So, notation for evaluating at x equals x naught is this. So for this notation, it's really easy. F prime of x naught, you just put it in like you were doing regular function notation. For the others, I need to include a new symbol. So dy dx with this vertical line, which means evaluated when or evaluated at x equals x naught. And I'm going to use that for any of these. So if I want to use this, df dx evaluated at x equals x naught, or the derivative with respect to x of f of x evaluated at x equals x naught. So let's see a couple of examples. First example is this, and the way I'm going to do this is sketch a graph of x cubed. Now, it's going to be an ugly sketch doing it on here. The more accurate your sketch, do it on graph paper, all of that stuff, the more accurate you can estimate this. So there's my axes. I'll put some scale to this. So 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. And 1, 2, 3, 4, 5. And I know that x cubed goes through 0, 0, 1, 1, 2, 8, which is going to be up here somewhere, -1, -1, and -2, -8. Now if I sketch this curve, and I'll try to do it as carefully as possible, it's a little bit hard to do it with this, it's going to look like this. And I want to find or estimate this, so I look at this point here, draw what I think the tangent line is going to look like. So coming in this case, brushing up at that point, and then coming here. It will eventually intersect over here. And I just count the slope. And this slope looks like up 3 over 1. So I will say that f prime of 1 is approximately 3, or 3 over 1. Now, what if I wanted to actually find some equations for tangent and normal lines? Well, I'll start off the same way. Eventually we'll come up with a way to do this without having to graph it, but I'll start off the same way for now. So, draw some axes. Again, please do it more carefully than I'm doing here. This is just to get the idea across, to show it can be done even without nice graph paper or graphing calculator, but take your time. Getting the graph correct is a big portion of this. So we have negative 1, 1, negative 2, 4. We have 1, 1, and 2, 4. And so here looks like my function. Now, in order to find the equation of a line, I need two things. I need the point, and I need the slope. The point we can just get from the function, so I can just do g of negative 1, which is negative 1 squared, which is 1. And that means my point is negative 1, 1. The slope I get from the derivative, so I'll try g prime of negative 1. And for now, I don't have any better method. In a little future video, we'll have a much better method. But I'll look over here to the graph, and I say, okay, I want to make it tangent to this point, or tangent at this point. That's terrible. Let me try to draw this better. So I go through there, and here's my line. And my slope here looks like negative 2 over 1, so negative 2. And I take these pieces, and I'm just going to do the easiest form I can think of, which is point slope form, y equals mx minus x naught plus y naught. And so for the tangent line, y equals, the slope is equal to this slope, negative 2, x, I'm going to use this point, so minus negative 1 means plus 1, plus 1. And for the normal line, well, I'm going to use the same point, so this over here, this portion of the equation will be the same, but I want it perpendicular, so I'll use the opposite reciprocal slope. So instead of negative 2, change the sign, flip the slope, I get 1/2 x plus 1 plus 1. I hope that helped introduce derivatives. Feel free to comment below with any questions, and we'll get into some more of this stuff in later videos.